Okay, we're going to get radiators today? We're going to learn about radiators?
Oh, video.
Yeah.
Say we should be building one. You should teach us.
Yeah.
You know me. I don't think I know anybody. Am I missing any previous engagements that I should know? Oh, you're recording this.
Yeah, we'll send you a video.
I'll keep it clean.
Oh, don't do that.
I was just saying, no.
My name's Tom DeWitt, and I was the owner of the company. I sold the business 3 years ago in 2015 to a company called AFCO Racing. They're out of Boonville, Indiana. They're famous for the shocks and circle track, dirt track racing, sprint car. They build a lot of stuff, and they're our corporate owner now. I sold the company and signed a 3-year agreement with them to stay on board as an engineer consultant to keep things going. And I just re-upped the contract another 3 years. So I started building reproduction parts for Corvettes. I'm talking about my hobby of building cars. When I started restoring Corvettes when I was probably 17, 18 years old, doing body and paint work for guys to make ends meet. You know, I didn't have a great job, but needed a second income and trying to get ahead. I was doing paint and fiberglass work, and then I bought that split window Corvette and I needed a radiator for it, and then GM discontinued it. And I knew because of the hobby, the restoration market, I thought, the hobby is not going to live with this part that being not available. As you know, that's not an option in Corvettes. When you can't have the original, you can imagine every original mid-year Corvette driving around with the wrong radiator in it. So I knew somebody was going to do it, and it's a high-ticket item. You know, the radiators, when GM discontinued them in 1984, they were $655. And who's got one of those old GM price books that you can get from the...
And it was $84.
Huh?
$1984.
1984.
And dollars. That's dollars.
Yeah, $655 that far back. Imagine what it would be if GM still made it. It'd be about $5,000 for it really is. Yeah. You know? And so it was a high-ticket item. I knew that if somebody was successful in making that radiator, and this is a long story, I won't bore you, but I got in cahoots with Harrison Radiator, 1,000 calls, we ended up tooling the radiator up, and we made it in Venezuela, and that turned out to be a disaster. We pulled the tooling out of Venezuela, brought it to the United States, and a company over in Dearborn was making it for me, Livernois Engineering. And then they closed their plant, and I went around the country and basically, you know, burned my bridge at every place that they all thought they wanted to do it, but found out it was such a quirky project that nobody wanted to do it. And I was having trouble getting this thing brazed, and so I was really frustrated. I started getting quotes on furnaces, and I found out the furnaces were like $1.5 million. So that was not in the cards. And one day I got a call from a guy, and he says, "Hey, you've been interested in the furnace? We just built a furnace for a company, and they went out of business before we could even sell it to them." So he says, "I'll give it to you for 50 cents on the dollar." So there it is. I bought that furnace before I had this building. And so I bought that furnace, and I thought, okay, now I need a building to put it in. So then I bought this building. We moved out of the barn in 2007, so we've been here about 12 years. We moved out of 2,400 square feet into 24,000. So when we moved in here, we thought, what are we going to do with all this space? I rented the front section up here to a company for 4 years, and then we just kept growing and growing and growing. Then we had to kick them out, and we took over the whole building. So that's a little bit of the history of how we got there. Like I said, in 2015, I started thinking about retirement. The original staff is still here. It's been a real good relationship. Nothing's really changed. AFCO does make radiators too. One of the things that it's kind of like behind the scenes is that nobody has this equipment. There's a lot of different companies. I'm sure you heard the names like Griffin and Be Cool and on and on and on and on. When I started this, there was probably 10 different companies that build aluminum radiators. Now there's probably around 40. Everybody looked at this and thought, wow, this is a really lucrative business. These radiators sell for $500, I can buy a core for $100 and put tanks on it and double my money, and all you need is a welder and a bender, and you can start up a radiator company in a garage. So there's a lot of different companies that are popping up, but the one thing that they all need to build a radiator is a core. This is a core, or actually it would be if it had all the parts in it, but there's headers on the side that take the collection of all the tubes. This would be a single row core, and it's the core that dictates how good the radiator works. And I can braze a bad core, trust me. If I wanted to try to build a bad core, I can make a bad core and it'll look just like a good one, but it won't dissipate heat. And the reason being is that when this brazes together, all of the material on this is a cladded material, it's not just aluminum. The surface has a secondary layer of a lower melting point alloy. So when it goes through the furnace, the surface of it puddles up. It actually looks very rough. Like, you also bond all the fin together to the tube, and that's where the heat transfer takes place. If you just stuff fin in here and you don't weld it to the tube, there's no heat transfer from the tube to the fin, and that's how you get the heat out. The water goes through there, transfers to the tube, transfers to the fin, transfers to the air. So the first stage in here is the fluxer. That's that big tank right there. We got a slurry tank out in front that just mixes the white powder, the flux with water. It goes through the furnace, or it goes through the fluxer, and gets sprayed. It's nothing more than like a car wash. It blows on the liquid and then blows off the water, leaving the white dust. And what that does is that gets the flux into the core. If you didn't get the flux down in here between the tubes, the fin wouldn't bond to it when it melts, and then you're not going to have a good transition of heat. And a lot of times what we'll do is self-destruct the core. We'll cut it right in half to check the fin bond through and through. Having it just on the edge of the surface isn't good enough. So you can't buy a core and go, well, I'm going to check it, make sure it's a good one. All you're checking is the front. What I wanted to have full control of our quality. I wanted to know that what we were sending out was a good quality product. So we started making our own cores, and it was part of my business plan. I was hoping that I could get our competitors to buy the cores from us. And we got 90% of them to do it. Some of them were a little reluctant because we were a competitor and they thought we were going to steal technology, but after a while we kind of made things marry up. So I would say probably 50% of the cores that we braze, we assemble and braze, go to other companies that build radiators. They go out here, they come out the end and go into a box and out the door. The easel in the back is a fixture that actually is designed to make that mid-year Corvette radiator complement. So you go from the basic operation to the table to this a little bit higher technology with a brazing fixture. I bought this from Visteon, and it was designed to build something else, and I tweaked it and tailored it. Let's see if we can actually demo. What this is just a tube drop system. As you can see, it's a mechanically driven system based on gears and timing, and it's a little bit limited because if anything gets off on this, that's part of the problem. I like some of the things about this machine, and I didn't like some of the things of this machine. So anyway, what happens here is this drops all the tubes down, and then while that's going, this machine is running, and it takes this, don't touch this, it's only 5,006, so it's thinner than a razor blade.
Ooh.
And it rolls the fin, goes through this corrugation setup, and it makes fin. And this little machine I developed, this is part of my old engineering background, is it just ejects the fin into a tray, and then when he's all done, he takes the tray with the fin and shoves it into the core, And so this is a little bit more automated. And then when he gets that, he puts these clamps on it to hold it all together. They got 2 of them. They'll bring it over here, and the second guy, this is a 2-man operation, the second guy just pop, 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 and he puts the header on it. Lines it all up. Kind of amazing that you can get 100 tubes to line up.
Yeah. Really?
See the belt is still going. That's about the brazing speed it goes. It goes about a foot a minute. It takes about an hour to get through here and fully cooked. This is just a cool down fan that blows up. Once it comes out, it blows right through it, just like a radiator, and it cools just like that. And then it has the bands and the clamps on it. The guys will take it off and inspect it. There's a little light tunnel on or thing. What he does is he bolts it up on there like this, and if there's any leaks shining through, you got a problem. We light check every one of them that we sell, and like I said, half of what we sell just like this. The other half we actually use. Now, if we use it, they get liquid tested. We're going to cap them, turn it into a radiator. We call this the furnace, and the next one is the oven. The oven actually just is a dehydration device that burns off any leftover water that's from the fluxing process. It's a dryer, basically. And then the fluxer on the beginning, and the very first item is the water tank. These are the top plates to the mid-year radiator sitting here getting dirty. You see every one of them has the GM part number in it.
Cool.
And then when we know what it's going to be, we date code them after the fact.
Stamp Harrison.
Well, Harrison isn't stamped in there.
Oh, isn't it? Oh, I know. Yeah.
But we do on the surge tanks. Yeah. What it does is, aluminum will oxidize like instantly. The longer you have it out, the more white it gets and tarnished it gets. And it doesn't really do anything. What it does is it removes that oxide layer. That actually melts first before the clad does. So it melts at, say, 900 degrees, and then the clad melts at 1,000 degrees. When that melts, it briefly removes the oxide layer off the aluminum, so the aluminum is fresh and virgin, clean. So that promotes the capillary action of the tubes the clad being drawn into there. And this is actually, what you didn't see, is this is a ready-to-go core. If I cut those bands, this whole thing would fall apart.
Wow.
So none of these tubes are brazed in. When we're ready to braze, we'll have probably 9 carts out here, just cores piled up all over the place ready for a braze day. We call this the brazing side for obvious reason. This is the fabrication side. We have 5 TIG welding tables, guys that do nothing but TIG weld all day long. And then on the end there, we actually have a MIG welding robot that does some robot welding for us. And this is what I was talking about, the mid-year radiator, Corvette radiator. It's very unique because it does not have one of these. That's the header that's on, there's a brass copper radiator, built the same way as an aluminum radiator, but they all have headers. You see how a stacked plate aluminum radiator, what happens is it doesn't look like much of a passageway, but this little bead all the way around here is what keeps that radiator from leaking. And these little beads in here prevent it from ballooning and pulling apart. So when I put this one to that one, you create a passageway in between. And that creates a tube or a flow path. And if you think about it, this thing could leak anywhere all the way around this part. And we have 56 of them in there. And that brazes down that valley, leak-free to hold 25-30 PSI on every one of them. And in between the plates, where they go like this. Every one of those is leak-free. And all of these joints, this tank and this tank is brazed down the top. It's 100% cap braze, no welding on it at all. And this was the very first radiator that I made, the most difficult one. And the reason that a lot of people, you know, the argument of aluminum and copper and brass will go on forever and ever, because how many engineers we got here? Okay, so you all know copper is a better conductor for electricity than it is for heat, right? So why does aluminum work better if copper is a better conductor? Well, it's not about material. Copper is a better conductor, and if you built a radiator out of aluminum, out of copper, like we do aluminum, then it would be better, but it would also weigh 100 pounds. Okay, and that was the dilemma. When aluminum came around, the engineers said, "Well, how do we get wider tubes?" This is a 4-core, right?
4-row.
4-row. Yeah, I'm trying to keep that term came from our dads and our uncles and our grandpas, so I'm trying to teach you old guys, so you teach the new generation, and we quit using the wrong term. But yeah, this is a 4-row copper radiator, and the tubes are probably around 3/8 of an inch. So what you have is you have 3/8, a 1/4 inch of dead space, 3/8, a 1/4 inch of dead space, 3/8, a 1/4 inch of dead space. So you got a lot of dead space. So the way they concluded when they said, well, how do we make a better radiator? So we'll make wider tubes. Well, when you make wider tubes, you get less dead space, but they also weigh more, okay? So instead of a 4-row, most of your radiators are 2-row. And they said, well, all right, how do we get more tubes in there? Well, you shorten the fin. You see the distance between, we use a 3/8 fin on our radiators. And now it's even getting down to 1/4. You see the gap in between?
That's the
Yeah, the
distance.
gap. So yeah, I mean, look at the center. How many more tubes? There's probably 10 more tubes in an aluminum radiator than there is in a copper one. If I built a copper radiator on that, it would weigh, like I said, 100-pound radiator. But it would cool like a son of a bitch. Right? Okay? So it has nothing to do with the material. Copper is a better conductor. And the other disadvantage of a copper brass radiator is it's 4 different metals. So my aluminum, this radiator is 100% aluminum, and the transfer from the tube to the fin is aluminum to aluminum. Whereas this radiator has steel side channels, it has brass tanks, it has copper tubes, and it has lead insulating, soldering the fin to the tube. And lead is a horrible insulator. So the heat transfer between the fin and the copper fin and the copper tube is not copper to copper. It's very poor heat transition. So why aluminum works better is because of the design, not the material and the way it's made. This is 4 different metals, old technology, new technology. And if you look at some of the radiators in the newer cars, like the late model, everything built in the last 25, 30 years is now a fatter single row. They're using these wafer thin, so you notice this is a 1-inch. That's a 1-inch tube. This is 1 1/4 inches. Okay? You'll see a lot of radiators built today with a single row 1 1/4 inch radiator and a cooling 500 horsepower. This is, and then we get a lot of radiators where they have to be fabricated. And so this one's a fabricated one that's just made out of sheet metal. And you can see it has multiple pieces in it. There's one piece, there's another piece, and then another piece. And that's for the corporate headquarters. Somebody painted the logo on upside down. That won't be received well.
Or at all.
When you look at it, is when we do have one of the this is one of our form tanks. When we do a form tank, the nice part about it is all the parts are press formed and repeatable. The header is obviously the same size. The tank is the same size every single time we make this radiator. So what it allows us to do is to put this into the robot and weld that all the way around. That's a robotic MIG weld. It's done by that machine. And it looks like TIG, but it's not. It's actually wire fed.
It does all the welding?
It does, well, it does the tank. The guy will come back and put the tubes in it.
Oh, okay.
We don't go around the tubes.
Is that spool-fed MIG welder?
Yeah.
How many tubes are in this?
That's a double row.
Double row.
1 inch.
1 inch, okay.
Yeah, most of our radiators are, the standard is a double row 1 inch. Then we have what we call the HP version is a double row 1 1/4 inch. Every radiator we make comes with the option of, it's a curse and a blessing because every radiator model turns into 8 part numbers. We have the manual, the automatic. We have the inch tube, the 1 1/4 inch. We have the natural finish in the black, and we have the manual and the automatic. Same radiator, eight times for the one model. And then you take all the models we make times 8, and you got a crap load of part numbers. Just like the Harrison radiator, these go inside the radiator. You'll never see them. The only thing you'll see coming out for automatics is 2 little holes. That's the robotic arm. And then I'll take you to the R&D department. We're licensed by General Motors to reproduce the original Corvette surge tanks. And what they were is just made off the original dies. And so we make 3 different versions of it. From the solid axle 61, 62 to the mid-year and then the think of our company as the old radiator guys, you know, the surge tank and the mid-year radiators, when the reality is that we've been the leader in every one of the new generations. When C4 came out, it was our most popular radiator. We were outselling more C4 radiators than we were plate radiators, probably 2 to 1. And then when C5 came out, C5 became our most popular radiator. And then 6, and we're hoping for 7. And that's the bulk of our business is late model radiators. And the reason is that, like I said, is they build these plastic tank thin, they're so marginal radiators that they're barely enough to keep the car cool under just normal driving conditions, you know. And when the radiator degrades either inside from corrosion or, you know, crap in the inside, they start to get hardening of the arteries or what have you. You start to see the temperature rise. If you start to get external, which is real common because they're floor sweepers, you know, they'll pick up leaves and grass and McDonald's bags and straw wrappers, and you get all this crap stuffed up in there, and they don't get as much air, then the temperature rises some more. You've got to constantly clean that crap out. So they're not robust systems. They're very, very marginal. Well, the first thing these guys do is modify these cars. They add even more horsepower to them. And so radiators are real popular items on late model cars because they just didn't build enough radiator in them to, you know, are they enough for the average driver? Yeah. But when they start to degrade, they're not. If you race, they're not. If you modify it, they're not. So we sell quite a few of them. The C7 has had a lot of cooling issues in the press because they sold the car as a race car. You know, the old adage, we say the muscle era of the 60s. That's wrong. The muscle era is now.
Yeah.
You know, this car, this is a 2016, and it's 650 horsepower. Bone stock. I haven't done anything to this car other than the skeleton stickers. You know, I get asked all the time, how much radiator do I need? I got a 500 horsepower car. I'm like, you don't need any more than the old lady that's got 250 because you're not going to be going 500 horsepower all the time. You might go a whole shot and a burst and a little thing, but then you can let it cool down, you know. And driving around the city at 30 miles an hour with a 500 horsepower engine shouldn't burn up any more horsepower than a 250. Behind you there is my wind tunnel. That's a piece of it. When I put it all together, it's about 15 feet long.
Somebody here up.
Yeah, I got a big blower and I put a radiator at the end of it, and we got all kinds of thermocouples, and we hook it up, and I got my Poindexter lab coat on, and I look all
Oh, cool.
scientific. Everything you do with a radiator is a plus and a minus. You know, and that's why people are constantly trying to figure out how to get something more out of it. But just like I did, I went from a 1 1/4 to 175 on the thickness. I gave it more surface area, which is going to increase the overall surface heat rejection area. But I also increased the differential of the air pressure going in. It's going to be harder to push air through that depth of it. And yeah, you get everything that you change on a radiator is a plus and a minus. There's nothing that's going to be one-sided of the equal side. This used to stand upright like a drafting board, and so I cut it down, made this angled base so we could lay it down. And this is to build single row, and this is the fin machine, and I buy that, and I make this. I can set on here whatever I want as far as the length of the fin and the number of pieces. So I know a full radiator is going to take 43.
You didn't say city of riches.
The tray bed below moves up one. Looks like it's just barely getting in there though. The first tray will be all the way out here on these rails for the operator to grab. That's my invention. Yeah, we're getting pretty close to it jamming up. What? It's still falling in.
As soon as it moves, it drops in. Yeah, it catches it on the front end of it, and then once it moves, it drops.
Simultaneous work. What's that? That's right. Make it? We made it.
All right.
Must have been this car club aura here.
That's your good luck.